Welcome back to JK Chemistry. Today we are going to discuss the problem. So the main concept regarding with this problem is that Pinacol-Pinacolone rearrangement reaction. You know the starting material for the Pinacol-Pinacolone rearrangement is that Pinacol. That is nothing but 1,2-diol. So you will end up with a Pinacolone. Okay, this is the Pinacolone structure. Okay, what is the general mechanism? It is a simple mechanism. First of all, you have 1,2-diol. That is the starting material for this reaction. And what is the key point to identify this reaction is that 1,2-diol. So you should have 1,2-diol and an acidic condition. Okay, it can either be a mineral acid or Lewis acid. Okay, so first protonation of one of the OH group takes place. So attack, okay, it get protonated. Now it is highly unstable, so you need to break this bond in order to nullify this positive charge. So shift, so you will end up with the carbocation. That is the important intermediate in this reaction. But in this rearrangement, what will happen is that this will undergo some kind of rearrangement. It is nothing but 1,2-alkyl shift. That is nothing but 1,2-alkyl shift. Okay, so for that you have OH group in the second position. So this OH sigma bond shift simultaneously, one of the alkyl group get migrated to the carbocation. So you represented in this kind of arrow. So that means this is migrated from here to there. Okay, that is 1,2-alkyl shift. That shift mainly depend upon the migration tendency, and moreover, since it is symmetric diol, if you have asymmetric, then the protonation is mainly depend upon the stability of carbocation, and finally you will end up with the wonderful product called Pinacolone. Now we move on to the given problem. This is our given problem. So first reagent is acidic condition, that means, and your starting material is 1,2-diol, that means it is Pinacol-Pinacolone rearrangement. Next reagent is the well-known sodium borohydrate, that is reducing agent, so reduction. Then third ring is acidic condition. So let's see what kind of a reaction will takes place. Generally, if acidic condition, you can have some kind of rearrangement. Okay, so it is given that first one is Pinacol-Pinacolone rearrangement, second one is reduction, third one is wagner-meerwein rearrangement. So let's move on to mechanism. So first, your starting material is this. So as we mentioned earlier, it will undergo, since it is symmetrical, one of the OH will undergo protonation, okay, attack, and dehydration, so shift, okay, you will get carbocation. And this is the most important step. Okay, initially we had a shift of alkyl group. Now there is no any kind of alkyl group, but here instead of alkyl group you can have ring residue. So ring residue will migrate from first to carbocation position. So this kind of migration takes place. So shift, okay, so the green colored one is your ring residue. So what will happen is that your 4-membered ring get converted into 5-membered ring. I can give the number 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So you can have second position, there is a keto function group. This is the peculiarity of this kind of bi-alicyclic compound. So if you have this kind of symmetric, so you will suppose it is 4-membered, you can have 5-membered, moreover second position having a keto function group. Okay, so the first rearrangement procedure is over, that is Pinacol-Pinacolone rearrangement. Second one is, we know that well-known reduction. So this product will undergo reduction. So sodium borohydrate furnish H- ion, so attack shift, okay, so you can have O-, it will undergo protonation, you will get alcohol. Okay, so this is the second reagent utility. And third reagent, again proton comes to the picture. We know that this is OH, so it will undergo protonation. We know that it will undergo dehydration, elimination of H2O. Now you will end up with the carbocation. Okay, now this is your carbocation. Now what will happen? So this carbocation can stabilize several respects. Okay, so this is our given carbocation. So it can stabilize by using this hydrogen. This hydrogen, and you can have this alkene, but this is not at all the major product. That is the thing, it will undergo a rearrangement, that is nothing but Wagner-Meerwein rearrangement, or simply it is 1,2 alkyl shift, 1,2 alkyl shift, 1,2 alkyl shift. So, and the moreover the driving force is that we know that here we can have a 4-membered ring. So if you expand this 4-membered ring, you can have a reduction of ring strain reduction. That is the main driving force for this rearrangement. So earlier I have shown an alkene, so here you can have a driving force to produce more stable ring. That's why ring expansion takes place. So this ring residue get migrated to this position, then this 4-membered get converted to a 5-membered ring. Okay, and here you can have this position have a carbocation, so that is here you can have a carbocation. Okay, finally here you can have a hydrogen, it will undergo deprotonation and you will end up with this product. Okay, this is your answer. Okay, this is your answer in option, I think it is C. Okay, ready? Okay, fine. So I can conclude some conclusion regarding with this kind of symmetric bicyclic compound, alicyclic rings. Okay, so if you have 2 3-membered ring, so interestingly your one of the ring get converted to 4-membered ring, and you will end up with a spirane ring, spirane. Okay, so initially you can have a bond between these 2 rings, but it becomes a spirane. One of the ring become 4-membered ring, and be careful that you can have a keto function group at the second position. From the ring junction you can have a keto function group. Similarly, suppose you have 4-membered ring, one of the 4 get converted to 5-membered ring, and second position having keto function group. If you have 2 5-membered ring, one of the 5-membered ring converted to 6-membered ring, and second position having keto function group. If you have 2 6-membered ring, okay, one of the 6-membered get converted to 7-membered ring, and you have a keto function group at the second position. Okay, so that is about symmetric rings. If you have asymmetry 1 4 3 and 1 4, what will happen? Interestingly, ring expansion takes place at small ring, that is 3-membered ring. So that means 3-membered ring get converted to 4-membered ring, and second position having keto function group. And 4 and 5, clearly ring strain is more in 4-membered ring, it get converted to 5-membered ring, and second position having keto function group. 6 and 5, clearly 5 get converted to 6, second position having keto function group. So this is a overall summary. So you can simply answer this question without doing mechanism, but you have to do mechanism. You have to know mechanism, that is the charm of this mechanism in this scenario. So you can have multiple steps, so you know about the mechanism. Okay, clear? Thank you, take care.